Let us now learn about the finite element method. This is a very powerful technique to solve partial differential equations, and it appears in many fields of engineering to model very complex objects. And before we go into FEM, let us discuss basis functions. And you will see the concept of basis functions will eventually lead you to finite element methods. And let us start with our favorite Poisson equation that we have solved in the last few lectures using finite difference methods. But now we will solve this using basis functions. And you can choose a set of basis functions. They can be any analytic functions or discrete functions, whatever you choose. And let us call these phi1, phi2 up to phi n. So there are n basis functions in these sets. It's like a Hilbert space. I mean, I'm sure you have studied this in your linear algebra math courses. You can treat it as a set of vectors, basically. And so from the Poisson equation, your input variable is the charge density rho, and your output variable is the potential, electrostatic potential V. And you have to express both of these now in terms of these basis functions. And I will over here I show rho, the charge density, as a function of the charge density as a linear combination of the basis functions. The coefficients are represented by b sub I. And because you know these basis functions, phi I, you have chosen them yourself. And you know that rho, the charge density that is given to you in the problem. So you can easily find these coefficients b sub I. So the input variable is known in terms of basis functions. Now what about the output variable? So you can again write it as a linear combination in your basis set. In this case, the coefficients are given by a sub I. And because you don't know V, you also don't know these a sub i's. You of course know the phi sub i's. Those are your basis functions that you have chosen. Now if I plug this into the Poisson equation, the equation becomes something like this, shown here. Right? So the red color represents the variables that I have substituted. Now you can multiply both sides of this equation with one of the basis functions from your tests from your set, basically. So let us choose phi j. J can be anything from 1 to n here. Now your equation is modified like this. And now you can see that this can be easily written as a matrix equation that is basically an equation that has matrix elements between two basis functions from the set phi I and phi j. So this equation here actually represents just one row of this matrix. And you can have a look at the elements. So the first row is the matrix element between basis function 1 and itself, 1 and 1. By OP, I mean the operator. The operator could be anything. For example, I mean, if you write the left-hand side of the Poisson equation as a matrix, then the operator is this delta square operator. Or if you if you represent the right-hand side of the Poisson equation rho, then your operator could be a constant like the charge density rho itself. But the point is that you can represent either the left hand or the right hand side with a matrix like this, for example. That represents the matrix element between any two basis functions. And this matrix is of size n by n, because you have your basis set has n vectors. And now let us look at some of the types of basis functions that are common. So if you are doing chemistry or atomic physics, two common types of basis functions are Slater type basis functions, also called Slater type orbitals, are also called, and there is also Gaussian functions. The Slater orbitals follows an exponential decay curve, e to the power minus alpha r. R is the position. It, uh, it decays radially, and alpha is the decay coefficient. So these are just forms of the Slater type orbitals. The Gaussian orbitals are similar, but they go as r squared. They decay as r squared of the distance. And they are used in many chemistry calculations or atomic physics calculations because they approximately represent uh, shapes of atomic orbitals, where you have a large electronic density at the center of the close to the atomic center, but that density decays as you go outward from the atom. But you can choose any type of basis functions. So over here, I show triangular basis functions. These are also called shape functions. They have particular shapes associated with them. And note here that each of these basis functions, they have a value of 1 at the node, what is called the node. The grid points are also called nodes. And they approach 0. They go to 0 at the adjacent nodes or adjacent grids. And this is just one particular form of choosing these basis functions. And also notice here that between two adjacent basis functions, there is a region of overlap, right? That is shared by both the basis functions. This is called the overlap region. And this means that the two basis functions have a non-zero matrix element between them. So if you integrate them over space, you don't get 0, you get something else. So these are also called non-orthogonal basis functions. But you can also have orthogonal basis functions, which in this case you see that there is no spatial overlap between two adjacent triangles. So if you integrate these basis functions over space, you get 0. So let us now look at this problem again. So we have derived this equation, a variant of the Poisson equation, by inserting the basis functions into the equations, and we multiply it with a test function. And now we will integrate both sides of the equation over all space. And then we exploit the condition that the matrix element, if you integrate one basis function, the product of a basis function and itself, you get 1. And if the basis functions are different, you have one basis function centered around one node and the other one in an adjacent node, then you get some overlap matrix S sub ij, overlap element. And so if your basis functions are very local, that is, if there is some overlap between one node and the adjacent node, but if you go 2 nodes away from the central node, then there is no overlap. Then you can make many of these elements Sij, the off-diagonal elements. You can make many of them to be 0. And so the matrix becomes very sparse. There are sparse meaning there are many elements that are 0 and do not need to be stored. So sparse matrices are very useful. They can be solved efficiently in many problems. So we want to represent our problems, our PDEs, with sparse matrices as much as possible. We want to avoid dense matrices. Those are full matrices that has non-zero values for most of the elements. We don't want that type of elements. So we choose our basis functions in such a way that the matrix becomes very sparse. Now let us write this as a matrix. So if I pull these test functions inside the summation, I can write this as coefficient. So the del square is now a local operator over the basis functions. Let's write these matrix elements as Cij, that is the operator evaluated between basis functions I and j. And then my unknowns, the unknowns that I want to find out are the a sub I coefficients. And on the right hand side, I have these matrix elements between phi j and phi I. but the B sub i's are already known, as I have said before. And to recap, this represents one row of the matrix. And you can see that this can be written as an equation, linear equation of n unknowns, basically. So this equation is just that represents one row of the matrix, is a linear equation that has n unknowns, and the unknowns are the a sub i's. So there are n elements of a sub i's. And then for each row we have one equation, and we have n rows overall, so we have n equations. So we end up with a system of n unknowns and n equations. They are all linear equations, and we should be able to solve them. Now if we write this problem as a matrix, you can see that I have a n by n matrix which is represented by the elements c, I, j. And then I have the variables that I am solving for, a1 through n. And then I have my right hand side. I can write this as a product of an overlap matrix S and the coefficients b sub I, right, in a similar manner. Okay, so this is the idea behind basis functions. And now let me go to the finite element method. So the finite element method uses these basis functions, but the basis functions are primarily shape functions. For example, in 2 dimensions, they can be triangles or quadrilateral or anything else, as long as it is a 2D shape. And in 3D, you can have more complicated structures as shapes, like a tetrahedron, a pyramid, prism, or hexahedron, for example, or you can have other types of 3D shapes. And the idea in finite element is to construct a complex geometry by putting these basis functions or shape functions together. So over here you see a complex region in space, and you can actually discretize this space by putting together some triangular shapes, right? So this has triangular basis functions, this finite element. And each of these intersection points are called nodes. These are the nodes in the mesh. So the whole region is called mesh. When I have like discretized the space in this manner, it's called a mesh. And then each of these intersection points are called nodes. And each of these triangular shapes, they are called elements. So there are a finite number of these triangular shapes, so they are called finite elements. And so why do we bother about finite element? What are some of the advantages? And one advantage is the non-uniform meshing. So for example, on the left side, you see that the basis functions are very regular, and they do a good job in representing the function u, which is also smooth. But what if u was varying rapidly in some parts, in some regions of x, basically? The situation which is shown on the right side, you see that the function here, it varies very rapidly. Then you could make the mesh inhomogeneous. So over here in this regime, you see that the triangles are smaller in x. So you can easily play with the mesh and make it homogeneous, make it large or coarse in one region and very dense in another region. So this is one advantage of finite element. You can adjust the mesh size as you need. And notice that you are not actually using the values of the functions at the nodes, but you are actually integrating them over space, over each element, basically. So this actually helps because you have if you have some singularities, for example, a Coulomb charge or something similar, for example, the 1/r charge which blows up at r equal to 0. you can actually integrate over them, and so you can get rid of the singularities. So this is one advantage of the finite element method, that you can include local effects easily. It doesn't give you convergence error. The finite difference method, on the other hand, uh, is not that good for representing such cases when you have potential or some quantity that blows up in some region. So another advantage of the FEM mesh is what I have already shown you. You can construct very complicated geometries from these simple shapes. And over here I show some examples. This is a range that is discretized with a number of triangular meshes. Actually, this is in 3D, so I think the prism, an FEM of prism is used. And then on the right side, you see this fan blade. Uh, this is also discretized. This is probably just quadrilateral meshing. And then heat sink is shown on the bottom. Complicated structure is also can be constructed using finite elements. And on the right side, you see an aeroplane moving through air, and you can discretize both the surface of the aeroplane and the fluid that it is going through, in this case the air, with finite element, and study problems in fluid dynamics, for example, or aerodynamics that are relevant to aeronautical engineering. Another advantage of finite element is that adaptive and mixed meshes. We have already seen an example of adaptive mesh. For example, if the function is varying very rapidly in some region of space, then you can adjust the size of the meshes. This is called adaptive mesh. You can adapt your mesh size to capture rapid variations in the function. You can also use mixed meshes. So you can put together a triangle and a quadrilateral mesh together, as is done in this range. You can see that some regions have triangular meshing and some regions have quadrilateral meshing. This is also useful when you are solving some problems involving complex geometry. You can also deal with dissimilar materials or dissimilar geometries if you use such type of mixed meshes. And so, what is the advantage? Another advantage is that the finite element method enables you to represent a complicated system with a set of algebraic equations for a steady state problem. A steady state problem meaning when the problems are not varying with time. See, in that case, we have shown that you can represent the problem as a set of linear equations with n variables, and you have n unknowns. The matrices are also sparse, and you can easily solve them. And if you have transient problems that depend on the derivative of time, for example, then you can use the same method, but in that case you have some set of ordinary differential equations that you have to solve. Anyway, another advantage is that now there are actually many matured packages that you can just call, use and use functions from. There are a lot of very powerful built-in functions and classes which you can put together to easily construct various finite element meshes and solve very complex partial differential equations with this. And I have listed a few here, but there are many available if you look in the web.